Hi, my name is Jinshu.
Hi, I'm Nathan.
I'm working in pixel size and time frame downsampling and also working on quantizations.
And I worked on extra compression.
Hi, I'm Yizhao. I done the transmission part by increasing the baud rate.
Hi, I'm Minjia. I'm responsible for the receiving part and file detection.
When we receive the image, first thing we did is pixel-wise downsampling by skipping every d pixels. This will reduce our imaging size by d squared. In order to recover as much as possible to original image, we apply bilinear filter during reconstruction, since it worked the best among 3 different filters we have tried. After pixel-wise downsample, we did time-wise downsample by using PCA. First, we reshaped the image as 2D matrix. The first dimension is time, the other is concatenating length, width, and colors. Then we decompose 2D matrix using SVD and pick K principal components from our detection file function that picks optimal combination of K components and D downsample rate. This will reduce our imaging by frame over K factors. Then we quantize our PCA data. In order to obtain non-negative number, we shift our data by subtracting the minimum of our PCA data. By doing so, we only need to transmit minimum number instead of a whole matrix negative number index. Next, we multiply our PCA data with a constant so we can quantize our data with unsigned int8.
Alright, so you significantly reduced the file size, but you still need it to be a lot smaller. So, what are you going to do? Here come the ideas of lossless compression, where you take a file and you encode it in some way in which information is not lost. We initially tried some ideas with just file types that really didn't do very much. Then we looked into the idea of Huffman encoding. The idea here is to encode your characters with respect to their frequencies. If a character shows up very often, its code is much shorter. This will save space because you use less space for the characters that are much more frequent. After implementing this coding schema, we found that gzip performed the same thing virtually, and also did it slightly better, so it made Huffman encoding redundant. So all that work wasn't really too important, but it was still nice to know how Huffman encoding worked and useful for later parts of compression, as we'll see. After using gzip, our file size was still a little too large, so we decided to try to encode our information in a manner that would be more accommodating for gzip encoding. It would involve reducing the unique number of values, as well as reducing the change per value, because those increase the entropy, and an entropy encoding takes advantage of low entropy in the encoding. Note, the first PC vector was shaped very differently than other vectors, and also was weighted much more heavily, so we just decided not to mess with it for this encoding and accept that the size of that vector would just remain as it was. And that most of our information was stored in our PC v-vectors, which are displayed below. Taking a look at the visual representation of these vectors, we can see that there's a high amount of values clustered around the mean, which we can use to take advantage of how gzip encodes things, as discussed before. We considered several ideas when it came to making our vectors low entropy. The first idea was to simply quantize the values further, taking them to the nearest even value or nearest fifth value or some such. We found that this lowered the quality too much. The idea, which we came up with after looking at the shape of the vectors, was to take the mean of each vector and set values close enough to the mean to be that vector. This did help, but the big issue with it is that if there are a lot of values far away from the mean, you don't quantize those and you don't actually end up saving that much space. The final methodology that we ended up using was to take a histogram of each vector and apply the above idea of means to each of the bins. By making the bin size and threshold tunable, we were able to compress to precisely the size that we wanted once we had applied gzip.
This is our final demo. First, we load the image, and after finding the best combination of numbers of PCA vectors and the downsample rate, we compress and modulate the packets. Now the package has been generated. Then we start to transmit.
Now we are receiving packets, and at the same time we are decoding them. We have 34 packets in total, and we store the number in the destination part. After a few times, we'll receive all the packets. Okay, then we store the received packets in a gzip file and read it, read all the information we need to reconstruct the image. See, we got 3 monkeys.